Hey guys, welcome back to another video. In today's video, I'm going to be doing some additional practice problems on ARIO. This is again chapter 3 in most books, dealing with acids and bases. So hopefully you find this video helpful, and I'll get started. So these lists of questions, you can see the problem is up here. Asks, for each of the following compounds, 2 protons have been highlighted. In each case, determine which of the 2 protons is more acidic, and it gives us some lines for conjugate bases if we want to draw them. I won't be drawing them for each one, probably just if we have to decide by resonance. But if you're confused about this video, check out the video previous to this one where I break down the list of ARIO, atomic size, resonance, induction, and orbitals, and you'll get a really good depiction on what we're doing here. All right, so let's go through this first one. And again, I'm going to be using ARIO for to try to help me out for each of these. So let's look at A in ARIO. So atomic size or electronegativity. The 2 protons highlighted are both connected to an oxygen, so we can rule out A. Right there, the exact same compound, we can rule that out. Resonance, I'm always going to get back to and see if we have a difference in anything else, because resonance, it takes a little bit more thinking to do. For induction, we do have an induction factor. We do have some halogens pretty close to one of our protons that's highlighted, and we have another proton that's highlighted that doesn't have any halogens, that's making it more electronegative and more acidic. So I'm going to call this 1 and 2. I would say that proton 1 is better for induction. Orbitals are the exact same. Those oxygens are in the exact same scenario where they have full octets, so they're good there. So now, and I'll cross this out. So now the only thing we have to really decide is, does the resonance differ with any of these? And that will outrank the induction effect that we have here. So let me rewrite what the conjugate bases would be, and I'll erase this for the time being. So conjugate base number 1, let's just take away one of those protons. We would have a negative charge right here, and everything else stays the same. And then let's do the exact same thing, but the other proton. 1, 2, and this would have a negative charge. So those are the 2 conjugate bases if you take away one or the other proton. Now let's see if we can do resonance. For this one, the only possible thing, obviously this is the first one, the only possible thing we could think about doing is bringing a lone pair down on that bond. The only reason why we can't do that is that this carbon would have a filled octet, and it just wouldn't work for resonance. So this first structure cannot resonate. It only has its structure right here. So it only has one structure. For the second one though, we can do something else, right? We can push this lone pair onto that bond, and we can put one of these pi bonds up into that more electronegative atom, that oxygen up there. And I will quickly show what that will look like. Again, this would be a double bond now because we put one of those lone pairs on there. So it only has 2 sets of lone pairs now instead of 3. And then we pushed the double bond up into that oxygen, so it only has 1 bond, so that negative charge stays there. And that gives us our answer on which proton is more acidic, right? If this proton has more resonance than the other one, and there's no other factors, the atomic size is the same, then that is our more acidic proton. Even though the induction might be better on that one, the resonance outranks the induction because ARIO goes in that order of ARIO. All right, on to the next one. Let me rewrite ARIO. Let's start with A, atomic size. We have a hydrogen directly connected to an oxygen and a hydrogen directly connected to a carbon. So there is a difference there. The oxygen is better than the carbon because it's bigger and it's more electronegative. So right off the bat, I would say that this proton is more acidic. The only exception we would have here is if we have an sp hybridized proton. But since we don't have any triple bonds in this structure, we know that this has to be our answer and we can stop there. So even though there might be resonance with this, maybe that can resonate a little bit. If we have a bigger atom, then you can choose that atom. The only exception, as I highlighted in my previous video, is if we have a triple bond with a lone pair attached to it. That outranks anything. But we can say that this proton right here is more acidic than the other one. Okay. And just like I said about 10 seconds ago, we have this problem here. So this is an sp proton. So we have a triple bond. You can imagine if you try to draw out the conjugate base, you would have something like this, or you have a lone pair and a negative charge. So that proton outranks anything. So even though this hydrogen is directly connected to a nitrogen and this hydrogen is directly connected to a carbon, you might think to yourself, well, nitrogen is more electronegative than carbon. No, if you have a triple bond and that's an sp hybridized bond, that outranks anything. So that triple bond is our more acidic proton. All right. Now let's look at this one. Let me again rewrite ARIO and think about atomic size first of all. Both of these are directly connected to a carbon, so that doesn't change anything. Again, we'll think about resonance in a second. Induction, really nothing we can see here. There's no halogens. And orbitals, they're both sp3 for both. So the only thing that would change is the amount of resonance that these two can do. So let's write the conjugate bases and see if we can do resonance. I'll leave this one the same and put the lone pair on that proton. And then put the lone pair here, the hydrogen coming out. So resonance here, we can, well, there's only really one thing we can do. We can see if we can pull these lone pairs onto that bond right by the nitrogen. And for this one, it's the bond over to the nitrogen. We would need to think about, for this first structure, if I just want to stick with this first structure, we would want to think about this carbon, because if we pulled this lone pair onto this bond, then we'd be filling that carbon's octet. So we would have to pull this double bond onto the nitrogen. So let's see what that would do. I'll draw it down here. So we have 1, 2, 3, 4. Get a negative charge on the nitrogen. You'd have a double bond right here. So that's one resonance structure for that one. Let's look at this other one. If you pulled that bond in right there, that nitrogen would now have too many bonds. So we have one lone pair on that nitrogen. Can that lone pair go anywhere is really the question. I would say it can. I would say let's try to take that double bond and place it on this carbon to make it another lone pair. and then maybe this lone pair on that bond, but I'm not really sure that that works, but we can see, and we can kind of guess and see if it does. I'm not certain that it does, and maybe this is our factor that, you know, changes the acidity in both of these. Let's see what would happen. We have a double bond right there. This lone pair now goes on to this bond, and a lone pair here. Yeah, that doesn't make sense. So subsequently, we can't do resonance with, whoops, too far. With, we can't do any more resonance with that structure. So that means that this bond right here and this proton would be more acidic because it can actually resonate. Our other proton cannot resonate. It's too difficult. All right, let's go on to our next problem, and feel free to pause the video if you want more time, and then you can definitely unpause it and see if we get, you know, a similar answer. All right, I believe that's the exact same problem. Oh no, we got a nitrogen now here. So one difference is we have a nitrogen, and if we're dealing with a nitrogen and the other one's a carbon, our A is different. So we're dealing with a carbon versus a nitrogen, and that nitrogen is more electronegative. So our our more acidic proton is that one. That's a pretty standard, simple one. Okay. Now we have two of the same kind of atoms that our protons are attached to. So in the AN area, that's they're the exact same, right? We have two highlighted protons that are directly connected to the same atom, which is nitrogen. So nothing there. We won't think of resonance right now. We'll probably have to get back to it. Induction, really no induction effect, no halogens here, and we have the same orbitals. So we have a nitrogen that has fully octet. Okay, so let's think about resonance. That's going to be our defining factor here. So let me rewrite, oops, different color. Rewrite each conjugate base. This might take a few seconds. That's the first one. Then we gotta take off the hydrogen on this one, which yields a negative charge. And let's see what kind of resonance we can do. Again, there's a lone pair right there and a lone pair right there. So for this first one, let's try to do resonance. First one I see is that, well, the pretty much only one I see is you could put this lone pair on this bond and try to think about shifting one of those double bonds into a lone pair. So I would say, you know, this is the only double bond you can shift into a lone pair. I would try to shift it there. So what would that conjugate base look like? Let me give myself, hopefully I have enough room right here. Got a lone pair right there. Double bond to that nitrogen. And these two bonds right there. So that is a plausible resonance structure right there. We have the same formal charge for both of our resonance structures, and our nitrogen is back to normal. It has 3 bonds again. So this first hydrogen can do 2 resonance structures. Let me erase this and think about our other structure, our other proton, and see if it can resonate. Again, we'll do the same thing we did. We have that lone pair right here. But the difference is we don't have another double bond that we can kind of change up. This double bond and this double bond are too far away. So we can't actually do resonance. I'll show you why when I draw out this resonance structure. We can't actually do it. So we'd end up with a double bond right here and a hydrogen. Even though that's good, right? That's the nitrogen has its full octet now. It has 3 bonds. We started with a formal charge of -1, and now we have a formal charge of 0. In resonance, your formal charges stay the same. So we need that negative charge somewhere. And, another problem is this carbon now has a full octet. So that resonance structure is not observed. So this has, I guess you can call it one resonance structure. It only has one, structure it can do. So this proton is more acidic because it has more resonance. And that's the only difference between the two. All right. Feel free to pause this to kind of think about these questions, and then we can go over them. All right, so let's get started. This asks, for each pair of the compounds below, predict which one will be more acidic. So I would urge you guys to, think about a periodic table and think about, because a lot of these are which atom is bigger, and it's really trying to get into your brain that, the bigger and more electronegative the atom, the more acidic it'll be. So for this first one, I'm probably going to need a periodic table as well. We have iodine and bromine. So the periodic table, let me erase this. We have iodine and bromine. Iodine is bigger. It has more atomic size than bromine. So iodine would be the more acidic compound. This next one, sulfur, is bigger than oxygen on a periodic table. It has more atomic weight, atomic mass. So this one would be correct. Subsequently, we're still dealing with mass. Oxygen is more electronegative, and it has more atomic size than nitrogen. So oxygen and water would be more acidic than NH3, which you don't think about water really being acidic. But let's go to the next one, 3.31. We're not dealing with atomic size anymore. We're dealing with orbitals, right? That O in ARIO, ARIO. So we have to think about sp, sp2, and sp3. Remember, sp outranks sp2, and sp2 outranks sp3. So we have a triple bond, so that's an sp hybridized. And we have a double bond, and that's an sp2 hybridized. So that sp would outrank the sp2 because our structures here are the same. The only difference is the bonds. We have the exact same number of carbons. So this would be bigger. All right, for this one, you can, again, for any of these, you can draw out the conjugate bases if you want to draw out sulfur and nitrogen, what the conjugate bases would look like if you take away the protons for both. If that helps, you think about this. Let's look at nitrogen versus sulfur and determine, where's my periodic table? Determine which is bigger than the other. So it looks like we have nitrogen at 14 and sulfur at 32. Sulfur is bigger than nitrogen, so this would be more acidic. Okay. Let's look at this next one. We have exact same things here, but the only difference is the halogen that we're using. So again, let's look at a periodic table. We have chlorine and fluorine. Chlorine is bigger than fluorine. So the correct answer would be this first one. All right, so that wraps up the video. Hopefully this helped. I feel like these these questions were more in depth than the second slide that I had. So hopefully that helped, and I'll see you guys in the next video.